I think it's even more important to go out and vote, because then you're really honoring the veterans who gave up their lives to protect that very freedom that we have, guaranteed by the Constitution. So it really is important to go out and do that. Okay, now, having said that, we simply must start working. So we start this thing here. Even went through my patriotic spiel. Yeah. Okay? Ah, that's what's happening. So, okay, let's get that. All right, talking about the orbit of Venus. We enjoy talking about orbits because this is astronomy class after all. And so we have quite a circular orbit in the case of Venus. Its semi-major axis, as we saw, it's about 0.72 astronomical units. Not too much eccentricity, and what we like to do is be aware of the relationship between the period and the semi-major axis. I write this down every time we talk about an object orbiting the sun, because it has this uncanny ability to give us the semi-major axis if we know the period, or work in the opposite direction. So here, we take the semi-major axis as known, 0.72 astronomical units. So what we do is we use Kepler's third law to solve for the period of the orbit in Earth years. And to do that, we, as usual, take the square root of both sides, so this 3 power becomes a 3 halves power, which is 1.5. And if we plug in 0.72 for the semi-major axis, we get 0.611 Earth years. So the length of the year on Venus is about 61% of Earth's year. So that's up from about 25% of Earth's year in the case of Mercury, about 225 Earth days. Okay, both properties. Well, we've already seen the density is close to Earth's density, but let's go ahead and remind ourselves how this is actually computed. We take the radius, about 95% of Earth's radius, and the mass, about 82% of Earth's mass. And if we take these values and actually plug them into our standard formula, we get a volume that's, of course, just a little smaller than Earth's volume. We get 9.3 times 10 to the 26 cubic centimeters. And if we divide the total mass by the total volume, we get 5.2 grams per cubic centimeter. So again, the typical terrestrial planet density, very close to Earth's density, very close to Mercury's density. And we look at this number and we conclude that there's probably a lot of iron in this planet. Right? When you see a density that large for a terrestrial planet, the first conclusion that you reach is there's a lot of iron. Because if it was composed of surface rocks, it would have a low density like we saw for the moon. Right? The moon's density is only about 3.5 grams per cubic centimeter. And we concluded from that there wasn't much iron on the moon, anywhere in the moon, or anywhere we want to talk about. Okay, so this number tells us that Venus has a lot of iron. By itself, it doesn't tell us where the iron is. It could be uniformly spread through the planet, or it could be concentrated in a core. Whether it's uniformly spread through the planet or concentrated in the core, it'll still produce the same average density for the planet, as long as the iron is there somewhere. Now, of course, if we lay on top of that the fact that Venus is very close to the sun, probably had some radioactive minerals in it like the Earth did, we can conclude that Venus probably is highly differentiated, and therefore most of the iron probably actually is in the core, just as we saw in the case of the Earth and Mercury. So again, just to give you a contrast on that, when we move on to Mars, we'll see that it solidified too rapidly to actually be highly differentiated. So that'll be the first example of kind of breaking that pattern, having a dense iron core. All right, surface acceleration, again, we use this formula so much that every year a few students inevitably tattoo this on themselves. I don't officially sanction that, but it's a free country, I guess. This gives us a surface acceleration as a function of the gravitational constant, the mass of the planet, and the radius of the planet. So we can do this calculation now for Venus, as we've already done for Mercury and the Moon and the Earth. So here's a little compendium of the different results that we get. Our benchmark, of course, is the Earth, 9.8 meters per second squared. The Moon we saw was very low surface acceleration, only about 1/6. Mercury we saw was about 40% of Earth's surface acceleration. Well, Venus is rather close to Earth's. No surprise there, because it's got almost the same mass and radius as the Earth. So, we pop the numbers in the formula, we're going to get a similar result. So the acceleration on the surface of Venus is about 91% of the acceleration on the surface of the Earth. So if we bring our trusty spring scale with us, we would weigh on Venus about 91% of what we weigh on the Earth. All right, now rotation of Venus. Now, if we remember, in the case of Mercury, we had Schiaparelli, renowned Italian astronomer and wine connoisseur, thought that Mercury was actually in a tightly locked orbit. And you kind of expect that because Mercury is close to the Sun, so you figure the strong tidal effect would create a tightly locked orbit. And so, his imagination perhaps, was already had this idea, this suggestion in his mind, and he thought he saw features on Mercury that were spinning around. But we saw already that that's not the case with Mercury. So the question is, what are we going to see in the case of Venus? It's even tougher in the case of Venus, because you can't see the surface at all. And the cloud tops are very homogeneous looking. There's nothing, no dramatic feature that you can look at to actually deduce anything about the spin rate. But nonetheless, people use their imaginations and actually concluded that the spin rate of Venus was around 24 hours, similar to Earth. So again, this is kind of an anthropomorphization kind of thing. We reach a familiar conclusion in the face of something that's completely unknown. The actual answer wasn't revealed until the 1960s, just in the case of Mercury, using exactly the same technique, the Doppler radar technique, where we send out a radar signal of a known wavelength, and from the spin of the planet, the bounce back signal has some redshifting component, some blue shifting component, and from the amount of redshift and blue shift, we can deduce the actual spin rate of the planet. And what we find is that it's quite different than what we thought. Again, this is just the schematic idea of using the rotation to create this broadening. Again, same process that police radar scanner uses to measure speed, pretty much. Turns out that a sidereal day on Venus is 243 Earth days long, so it's even more radically strange than Mercury was, even, right? In the case of Mercury, what we found was a sidereal day on Mercury was 59 Earth days long, so about 2 of our months long. So on Mercury, every 2 months on Earth, Mercury is experiencing one sidereal day. Right? Well, if you look at Venus, now you're talking 243 Earth days, so that's something like around 8 months, right? So every 8 of our months, Mercury is just experiencing, Venus is just experiencing one sidereal day. And even more strangely, this is the first example of what we call a retrograde spin. So if we go way up to the North Celestial Pole and we look down at Venus, this is the first example of a planet that's not spinning counterclockwise. Mercury spins counterclockwise, the Earth spins counterclockwise. It will turn out that Mars spins counterclockwise. But Venus is actually spinning clockwise and very slowly as viewed from the North Celestial Pole. Right, so if we talk about solar days on Venus, it's a little bit complicated because of the fact that the rotation is even in the opposite sense that we're normally used to for a planet. But it turns out to be about 117 Earth days between the solar days. So this is again actually quite opposite even of Mercury. I mean, if you remember, the way it works on Mercury is that in two years on Mercury, you have 3 sidereal days or 1 solar day. And yet on Venus, so in other words, the solar day is actually a longer day than the sidereal day on Mercury. Here it's actually the opposite. The sidereal day is a lot longer than the solar day on Venus, and that's because of the opposite spin that we're seeing here. All right, so one can ask, of course, why? Well, in the first place, why does it have this retrograde kind of spin? It does go counter to virtually every other planet, with one other exception, that we see in the solar system. So this is an example of a couple of things. One is, it's an example of where we're going to surmise that a collision took place to explain this radically different pattern that we're seeing in the case of Venus' spin compared to almost any other spin. It breaks the pattern of regularity of spin that we see in the solar system. We don't think Venus was born this way with this kind of spin. We think it was actually hit. Probably much like the Earth was hit during the formation of our moon. But Venus was hit in such a way that its spin actually reversed direction. We don't think that happened with the Earth. And the other thing about this that we need to talk about is there anything special about these numbers? We found that there was something special about the spin and orbit periods on Mercury, because we were able to see this spin orbit. Oh, I know it's there. We see the spin orbit coupling on Mercury. So what's going on here? Okay, well, let's just start at 0 day here. And we will point our standard little stick there toward the sun, and it's also pointed towards the distant star, as usual. Now we proceed to let the orbit go, and as you see, the spin is clockwise, not counterclockwise. And what happens is that after 117 of Earth days, we actually achieve the next min. And you can see that's happening well short of a year. It's also well short of the next sidereal day. The reason I say that is because the stick has never pointed to the right again. It's rotating clockwise, and it's not pointing to the right since we started out. So this is one solar day after we started out. 117 Earth days is one Venus solar day, but we haven't hit a sidereal day yet. Let's let the process continue here. If we let the process continue, 243 Earth days since we began the process, we've now hit one sidereal day. So that's the 243 number. It's the sidereal rotation period, the stick pointing to the right. So the sidereal rotation period is 243 Earth days, but the orbital period is 225 Earth days, so the sidereal day is actually longer than a year on Venus. So this sounds kind of like a little bit of mumbo jumbo, and it doesn't make too much sense unless we start thinking about what could possibly cause an effect like this. We think it may have something to do with the gravitational pull of the Earth, because the Earth is the most massive body that's relatively close to Venus. The sun's too far away to exert a very strong tidal effect on Venus, but the Earth is actually closer to Venus than the sun is. Right? So let's look at what happens if we start with an inferior conjunction, which is when Venus is between the Earth and the sun at time 0 there. After one full rotation of one orbit of Venus, that's 225 Earth days. After one orbit of Venus, of course, Earth hasn't completed an orbit yet. Now, if we're waiting for the next inferior conjunction to occur, we have to wait for Venus to catch back up with the Earth, and that's actually 584 days. Okay, so 584 days, so what? That sounds like a pretty arbitrary number. But now, if we do the math, the 584 days, let's think about the relationship between that and the solar cycle, the solar day cycle. Well, that ratio happens to be almost exactly 5, right? Now, this is the relationship between inferior conjunctions and the length of the solar day on Venus. So, well, it's not exactly 5. It's not precisely an integer 5. So the fact that it's not exactly 5 means that it could actually be a coincidence, because usually when you see a resonance, it has to be an integer type of relationship, because that means that you get some kind of reinforcing force that keeps the relationship going forward. So this isn't exactly 5, but it's close. So we think there may be a spin-orbit resonance that relates to Venus and the Earth, but we really don't know for sure. But the one thing we are sure about is that the retrograde spin must be due to a massive impact in Venus's past. It survived a very, very violent relationship incident in the past, where we probably had a very large asteroid, or again, maybe even a Mars-sized body coming in, but instead of a glancing blow in the same direction that the planet is spinning, which we think happened with the Earth, it seems to have been a blow in the opposite direction that the planet was spinning. So it almost completely wiped out the planet's spin, and even started it spinning the opposite direction. So it probably had fast counterclockwise rotation of Venus initially, maybe with a period of 24 hours, something like the Earth's period. But after this incredibly violent impact, we have a Venus which has been clocked, spinning clockwise, slowly clockwise. It's probably, I would think that this impact was probably so violent it pretty much melted Venus, because if you're talking about, you're not going to take a solid body like that and hit it really hard and have it just start spinning the opposite way, like a top or something like that. You're going to basically pulverize it. This was an incredible kind of impact. So we think that that's what's happening to explain the rotation. Other oddities of Venus, we get into discussion of the atmosphere. Okay? Now this is actually another area where we were led to a false conclusion by a simple observation, which is the temperature of the top of the clouds. When we look at Venus, we're only seeing the top of the clouds because the planet's completely shrouded.